Hi, Calc 3 folks. Welcome to the online Project 4. There's no class meeting on Friday, February, 21st, 2020. So instead, you're going to be doing this project entirely online. So let's go ahead and get started so you can know what to do. So your job in this assignment is to obviously watch the video that you're watching and then address there's five questions that I ask you to submit here. You'll be submitting your responses in a written document. You can use either standard Microsoft Word or PDF, or you can just enter your responses in a text entry. Okay, so we're going to be studying something called the Cobb-Douglas model of productivity, and we're going to be finding some optimizations of it subject to a constraint, which is to say a constrained extrema, and we're going to be using the principles of Lagrange multipliers to find the maximum. We're not going to be using the algebraic techniques. We're going to be using the geometry of the Lagrange multipliers to do these calculations. So let's go ahead and get started and learn a little bit about the Cobb-Douglas production function. It's a standard multivariable function of productivity from econ classes. And despite the fact that it sounds complicated, it's actually really, really simple. So it's a functional form of a production function, widely used to represent the technological relationship between the amounts of two or more inputs. The inputs are usually capital and labor, and the amount of output that can be produced at these inputs. It was developed using statistical evidence between 1927 and 1947, but the reality is today it's actually considered a little bit dated. Mostly it's used to teach about multivariable functions. So here it is. The function is a dependent variable. Usually in econ they say y is a function of a constant. This is just a constant called the total productivity factor times the amount of labor raised to an exponent times the amount of capital raised to another exponent. For reasons that aren't really clear to me, these exponents alpha and beta are usually forced to sum to 1. It's called elasticity. We don't need to go into any of the econ details of this. The important thing to think about is that we have a production in an economic system is dependent on the labor and the capital. So productivity is a function of L and K. Y is a function of L and K. And that's kind of all you really need to know. Usually that's actually true, that you can measure productivity as a function of labor and capital. And then if labor and capital cost a certain amount, you might have some constraints on how much labor and how much capital you can afford, and therefore you want to optimize your balance on what you can spend on labor and capital. So we're going to be taking a look at that. The specific production model that we're going to use in this project is here. Y is a function of L and K. We're going to use the constant 0.5, and we're going to use exponents of 3/4 and 1/4. These are all changeable, so these three numbers, 0.5 is changeable, and 3/4 and 1/4 are changeable. Just the exponents always need to sum to 1. So why don't we go ahead and copy this. And I've got to actually open GeoGebra. And let's go ahead and create this function. GeoGebra allows you to use other variables besides x and y for independent variables for a multivariate function, but it can get a little confusing. The first one will be plotted as x, and the second one will be plotted as y. So we'll create this multivariable function. And I'm opening up the 3D view. And we can see that this is very similar to the Cobb-Douglas production model that we saw here. So looking at this picture a little bit more, we've got an x-axis here, L, it's an L-axis really, and a k-axis here, only positive numbers, 0 to 1. and then y is the z-axis, and so we've already reconstructed this. In fact, this is a very similar view to what the what's on Wikipedia there. So we've got L is our x-axis, K is our y-axis, capital, and Z, the blue axis, is productivity, the production of these inputs of labor and capital. So kind of cool. So what we're going to do, sorry about that. We're going to look at optimizing subject to some cost realities of labor and capital. So we're going to assume that the cost of labor is $200 per unit of labor. Usually it's unspecified what that means. Is that one person for one day, or one person for 1 month, or one person for 1 year? It's different depending on the setting. We're just going to leave it as, say, per day. The labor is $200 per day, and the capital expenses are $300 per day. It really doesn't matter. So if labor costs $200 and capital costs $300, let's try to think about how this represents a constraint. So what is your best guess estimate? So we don't need to be technical here, for the maxima of production, subject to the constraint that total labor and capital expenses are not to exceed $5,000. Well, let's go ahead and take a look at that. So let's see if we can write our constraint. So 0.2 times x, remember x was labor, plus 0.3 times y is not to exceed $5,000. So x is labor, y is capital. And if I zoom out a little bit, we can see our constraint on the amount of money that we can spend on labor and capital. $200 times the number of labor units plus $300 times the number of capital units is not to exceed $5,000. Everything here is in thousands. And so you can kind of eyeball it and say, okay, that the maximum productivity is going to be somewhere up here, but the thing is not symmetric. You can kind of see it pretty clearly. Like maybe your first guess about the production model was that it was actually symmetric, so you just follow along y equals x, but it doesn't appear to be doing that. So we would actually need to use a little bit of the principles of Lagrange multipliers. So what we're going to do is we're going to put a point on the production model, and then we're going to go ahead and calculate the partial derivatives. I'm just going to do them manually, because we don't need to necessarily use GeoGebra. So the partial derivative of y with respect to L is going to be 0.5 times 3/4 times L to the 3/4 minus 1 is -1/4, and k's exponent won't change. So there's y sub L. I'm going to go ahead and hide the partial derivative. And let's calculate the partial derivative with respect to k. Oops, yeah. So it'll be very similar. Let you think about it for a second. What's the partial derivative of y with respect to k? So treating L as a constant. So it is very similar to what we had before. But now we use the power rule on k to get a derivative of 1/4 times k to the -3/4. Because 1/4 take away 1 is -3/4. And now we're going to use these partial derivatives to build the gradient vector here at A, so we can take a look at when the gradient vector is perpendicular to the constraint. And what we're going to do with this is we're going to use it to make a best guess estimate for the maxima of production. Now what we're not doing is using the algebraic form of this. We're just using the geometry. So we're going to make a vector that starts at A and from A heads in the direction of y sub L of x of A, y of A, comma, y sub K of x of A, y of A. Cool. I'll leave that on the screen. Pause the video if you need another second to look at this. So just to talk about this a little bit, what we've done is we're making an arrow or a vector that starts at A and heads in the direction from A towards the gradient. Partial derivative with respect to L evaluated at the coordinates of A, and partial derivative with respect to K evaluated at the coordinates of A. So the vector is pretty small because the Cobb-Douglas function doesn't grow very much. So a pretty good trick here is to just put a little constant on it to make it a little bit bigger so that we can see it. And actually, looks like we need it to be a little bit bigger than that even. Okay, that's pretty good. So by just putting a constant here on the length of the gradient, that'll help us see a little bit more of what's going on. To see the gradient, because if we didn't extend it, we wouldn't be able to tell what the direction is more clearly. So remember, as we move A around, the gradient always points in the direction of steepest descent, but the principle of the Lagrange multipliers is that we can use the gradient as a tell for when we're at the maximum of the function subject to the constraint. So it's actually easier to look down on it from above. And it looks like the production is maximized on this constraint, something like that. It's a little tricky for me to tell. Somewhere around there. Our values x and y. Now we should double check that 20% of x and 30% of y is indeed 5. But it looks like production is about 6.51. So I've done the first question for you. It looks about 6.5 is our best estimate for the maxima of production subject to the constraint that labor plus capital does not exceed $5,000. We did not use technical Lagrange multipliers, we just used the principle of Lagrange multipliers. So what you're going to do on your own now is you're going to bump up the budget for labor and capital to 10,000, 20,000, and 40,000. 5,000 is unreasonable. By the way, the production is over the course of a year. So this was an unreasonable budget for labor and capital for 1 year. What you're going to do is you're going to just bump up the budget to 10,000, 20,000, and then 40,000 and answer what you find for the maximum there. And then as you do so, I ask that you answer if you see a trend forming in the rise in productivity as the budget for labor and capital increases. Hopefully you'll see a pretty easy trend to observe here. So that's all I'm asking you to do. This is actually easier than some of the stuff we've been doing algebraically, because now instead of having to do a Lagrange multiplier, what you're doing is you're just using the Lagrange multiplier principle to identify this maximum. You don't really need to use it. You could just kind of like look at it from here. But I find actually what's hard to do it this way is that it's hard, without the gradient vector, it's hard to make sure I stay on the constraint. To keep myself on the constraint, it's easier to look down on it from above and then pick off the maximum of the function from above by just paying attention to when the gradient becomes perpendicular to the constraint. Cool. So, yep, we've done the first question here. It's about 6.5. I'll ask for you to estimate the answers to these and then address what the trend is that you see. Take a guess about what the trend is, but you do not need to prove it. So if you're interested in learning more about the history, this function was first studied in the 20s, and it was refined and researched against statistical evidence. It is still a classic model in economics of productivity. However, it is a little bit dated now. We're not going to have a chance to understand this model more deeply in this class, but we will, however, return and use the method of Lagrange multipliers after break to take a look and see if we can figure out a way to get the algebra to find these exact values a little bit more accurately. If you want to take a shot at this, go ahead and do it now. It's kind of fun to see if you can get the algebra to work out. Even if you can't get the algebra to work out, see if you can sort of get GeoGebra to hack it to find the exact value. But if you can't, no big deal. We'll take a look at this later. Okay, so have a great break. Hope you enjoy this project, and I'll see you in March.